When x and y are independent random variables, the probability density function of their sum can be expressed in terms of the probability density functions of each of the random variables individually. So let's let x and y be independent random variables. And let's define the new random variable t to be their sum. Then the probability density function of t is, I'll write f sub capital T of little t for it. It's the integral as y goes from negative infinity to infinity of the density function of y. Sorry, let me do x first. Density function of x evaluated at t minus y times the density function of y dy. So this, notice this has an integral in it even though it's only a density function. Usually the density functions are things that we integrate to get the cumulative distribution function, but this has an integral in it already. So to see this, let's find the cumulative density function of t first. So the cumulative density function is the probability that x plus y is less than or equal to t. And that's the integral of the joint density function of f and y. Now these are independent, so we can just factor this right away. And let's see, the limits of integration are going to be, we could let y go from negative infinity to infinity, and then x is going to be constrained to go from negative infinity to t minus y. Because x is less than or equal to t minus the random variable y. dx dy. Alright, now this doesn't have any x's in it, so let's take it out. The integral is y goes from negative infinity to infinity of fy of y. The integral is x goes from negative infinity to t minus y fx of x dx. Now this has a y in it because of this limit of integration, so we can't move the dy over here. What is this? This is the probability that x is less than or equal to t, the number t minus little y, whatever that is, which is fx of t minus y. So that means what we have here is the integral as y goes from negative infinity to infinity of this density function times that cumulative distribution function. Let me write this one first. fx t minus y little fy of y dy. So, well, this might look a little unfinished like this, but really all we want is to get some expression for capital F of t that we can then differentiate to get little f of t. So now let's differentiate this. I'll erase this because we're just going to end up with it at the end of the proof anyway. Now the density function is d dt of capital Ft, which is the derivative of this integral. The integral is y goes to negative infinity to infinity, capital Fx t minus y, little fy of y, dy. Now differentiating with t has nothing to do with integrating dy, so we can move that inside the integral. So we have the integral dt of fx t minus y, fy of y, dy. This is the only thing that has the t's in it, so those are just constants as far as differentiating with t is concerned. Now capital F is a function of one variable. It was originally defined in terms of the variable x, but we have another variable in there for x. So when we take the derivative of this, we can use the chain rule and say it's the derivative of this, so little fx of t minus y, times the derivative of what's on the inside. Well, d dt of t minus y is just 1. And then we'll leave this here, fy of y dy. And that is the claimed integral that we get. So this is a formula that we can use for combining random variables to form a sum. I want to note, if x and y have the same distribution with different parameters, so they might both be uniform random variables, they might both be normal, they might both be Poisson. Then x plus y may or may not be the same type of random variable. If we had normal random variables together, we get another normal random variable, but that's not the same for all distributions. So we'll look at the different cases in different videos, one at a time. The end.